Hello everyone, let's look at some properties of conductors. We have already learned these properties in various contexts. Here we'll just summarize the properties once more. The first property is inside a conductor, electrostatic field is zero. To understand this, think of a conductor of a random shape. Suppose if this conductor is placed in an uniform electric field or any field for matter, a conductor basically means it contains free electrons. So what happens here is the electrons would distribute on this side and the protons on or the plus charge would be on this side, such that the effect of this would be zero. So here the charges would distribute in such a way that the field inside would be zero. That is called field inside would be zero. To understand a better way, we can think of any point here, a random point P here. If we draw a Gaussian surface around this or on this point P, there is a point P. Then if we use Gauss law for the surface, then from Gauss law, integral of E dot ds is equal to Q enclosed by epsilon naught. This surface doesn't enclose any charge, so this term is zero. That implies that this whole term is equal to 0. That would mean that E is equal to, or E inbuilt, I'll put E inbuilt here, is equal to 0. So electric field inside the conductor is 0 in static condition. Second point is electrostatic field is normal to the surface of a charged conductor at any point on the conductor. That is, if you have any conductor of any random shape as in given here, then the electrostatic field, if you put some charge onto it, then the charge would distribute such a way that the field at any point on the surface is normal to the surface. For example, here it is normal to the surface like this. Again, here it would be normal to the surface like this. Electric field at any point would be normal to the surface. That is because if the field was not normal, that is, if you look at its cross section, look at its top view from this, look at the top view of this part, just draw this, then if the field was not perpendicular, rather the field was aligned at an angle to the, say, normal, we call this as E, then this E will have two components. A component which is perpendicular to the surface, we'll call it as E perpendicular, and a component which is parallel to this surface, something like this. We'll have two components, we'll call it as E perpendicular and then E parallel. But if this component is present, if this is present, then the charges would still keep on moving. For example, think that this as a component like this, the charge will start to move, but the charges are already at rest, they're not moving any further at all. So from that we can say that electric field is always normal to the surface. This is not possible. That's the second point. Third point is the interior of a conductor can have no excess charge in static situation. Here it says excess charge. To understand this, let's think of a case where we take a conductor of a random shape as given earlier. Suppose, imagine that we keep on adding charges into the conductor. Now what happens is, because it's a conductor, the charges will start to move on the surface. So it'll keep on piling up here. If you keep on adding more charges, after a given point, the charges cannot be more piled up on the surface, and also the charges cannot leak into the atmosphere, because the atmosphere, which is air, is a bad conductor. So that way some charge may remain here also, but the extra charge will go to the surface. So as much as possible, the charge will start to spread out and many will go to surface also. That's the meaning of it. The excess charges would go to the surface. Fourth point is electrostatic potential is constant throughout the volume of the conductor and has same value as inside on its surface. So it means that the electrostatic potential is constant throughout the volume and has same value inside as well as the surface. Again here, if we take this case itself as a case of a conductor, we know that from the first point we learned that the electric field inside is 0. But we know that E is equal to minus of dV by dr. Since E is equal to 0, it means 0 is equal to minus of dV by dr. This implies that dV by dr is equal to 0. This would mean that this term here is a constant. Therefore, we can say that electric potential is a constant on the surface as well as it is same inside. For example, if you look at a point P here and a point Q here, since there is no field at all, then the work done to move from here to would be 0, because work is done against an opposing field or with the field. There is no field inside, so work done to go from point P to point Q would be 0. Recall that work done to go from initial point to final point is equal to Vf minus Vi. So work done to go from point P to point Q is equal to V potential point Q minus Vp, but this work done is 0. So therefore 0 is equal to Vq minus Vp, or Vp is equal to Vq. This is what is the meaning of it. Similarly, you can find out that the work done to go from the surface also here would be 0, because nothing is opposing it. So the potential at every point inside the conductor, whether it's a point P here or a point Q here or a point R here or some other point here or some point here, all those points will have same potential. For example, if the potential at this point R is say 5 volt, then everywhere inside the conductor or on the surface it will be 5 volt only. If the point is electric field at a point outside a charged conductor is given by this form, that is electric field outside a charged conductor is given by sigma by epsilon naught. You can again prove it also. For example, think of charged conductor like this. It has some charges present on its surface. Now here what we'll do is we take a Gaussian surface in this case. Let's assume that the surface is like a cylinder. Now this cylinder will have 3 faces. This is a top face, a circular base, this is one more base, and the curved section. Let us call this as say phase 1, this as phase 2, and the curved path as the phase 3 or surface 3. So the flux through first phase, that is E dot ds is equal to, keep in mind that the electric field at this point, if it's E, it will be perpendicular to the surface. It comes out like this. So in this case, the electric field and area vector are in the same direction. So angle between them would be 0. So just becomes E into ds. That is, it will be E into just ds. We'll drop the integration here. We'll just do for a small region, that is E into ds is the field here, because the angle between E and ds is 0. But this is the flux to the, say, first surface. Flux of second surface would be 0 because there is no field here. And flux of third surface is also equal to 0 because for third surface, look at this part of third surface, then the electric field is going out because the field is from here. This is the element. The area vector or the field goes out like this. But for this, area vector is going out like this. So angle between this field and area would be 0. So this goes away. Therefore, what we get is the total flux is equal to flux because of 1, 2 and 3 is equal to just E into ds. But from Gauss law, the flux is equal to charge enclosed by epsilon naught. Here it is charge on this given circular region, on this region. So if we assume that the surface charge density is sigma, then sigma is defined as charge by area. So from this, charge will be sigma into area. Therefore, it will be sigma into area is this part only, which is same as the top surface, that's the enclosed part, into ds by epsilon naught. This is obtained from definition of flux, and this is obtained from Gauss law. Equating 1 and 2, you can say that E into ds is sigma ds by epsilon naught. From this, ds gets cancelled, and finally what remains is E is equal to sigma by epsilon naught. So this is the field outside the, or this is the field because of a charged conductor. In terms of vector quantity, E is equal to sigma by epsilon naught into n cap, where n cap is normal to the surface. The last point is called as electrostatic shielding. Now, shielding is a common English word which means to protect. So what happens is, many times if you have a conductor, as seen in the first point earlier, and suppose if we apply an external electric field, then the charges would distribute in such a way that the charges would be minus on this side and it will be plus on this side, such that the net field inside would be 0. So E inside would be 0. Or we can take a case where there's something of this kind. We have a conductor. If we take a small, say, area out of it, if you have a cavity here, this is called as a cavity. Cavity means a small, say, open space or small volume removed from the material. Even here also, if we apply electric field, then the charges would distribute in such a way that electric field here is 0. So these conditions where the electric field is 0 or potential is 0, when nothing is placed here, so inside this point electric field is 0. So this principle or this phenomenon is called as electrostatic shielding, which means the conductor shields or protects the inner components from the outside electric field. It has many applications. One use of it is to protect sensitive electric instruments. We will do when we talk about ammeter and voltmeter. Now understand that this principle is used in protecting sensitive electrical equipments. Here, some examples are given up for shielding. As seen here, we have a source of an electric field, and then this is like a cage. You find that the person inside is safe from the outside electric field. Even here also, we have a case, we have a car, we have a source of electric field. By the principle of shielding the components inside, that is, the charge would distribute on the conductor such that the inside, like a cavity, the field is 0. This principle is called as electrostatic shielding.